Welcome to myprojectbuzzer.com. Here we discuss about new approach to VLSI buffer modeling considering overshooting effects. Today, CMOS technology has been got more popularity than the bipolar technology, especially for analog circuits to form the mixed signal systems. The industrial trend of this time wants to achieve the goal of minimum size of the chip. The most common used as amplifier is common emitter or common source that magnify and invert the input signal. Due to the reduction of gate oxide thickness of MOSFET gives the reduction tolerance of the MOSFET device for the higher voltage levels at the gate of MOSFET. It means that to reduce the maximum supply voltages VDD, it gives the helpful purpose. Due to the reduced supply voltage, analog designer have to face some common problems like input common mode range, output swing, and linearity of the device. In the resulting form, to implement the desired analog device, we apply the CMOS technology with low voltage and low power techniques. The second major aspect for the designer of analog circuit is to stand the circuit with low power dissipation, which is helpful to improve the battery life of the electronic devices. As the CMOS technology is scaled down to the nanometers and femtometers, the analog circuitry has to need to maintain its quality of performance for many parameters like device size, bias current, voltage, parasitic capacitance, and the voltage of supply voltages. This scaled down features of the CMOS technology and the reduced power dissipations is helpful to get the mixed mode type circuits, which is the combinations of analog circuitry and digital circuits. The proposed paper, which proposes with a new current leakage scheme. Buffer circuits are mostly used to run the large capacitive load at high speed. Here, rail-to-rail Class AB CMOS buffer is presented to derive large capacitive loads. Class AB buffer is also described already in background part. Class AB buffer amplifiers are mostly used in most analog circuitry. Class AB amplifiers are mainly used for low power consumption and to gain reduced crossover distortion. Here in our base paper we propose CMOS based buffer architectures in 19 nanometers and 65 nanometers and 45 nanometer technology. Here in the base paper shows the HSPICE simulation result, which will displays only the coding result and not displays the circuitry arrangement. So thus we using T-Spice or Tanner tool to visual the circuit implementations and final output waveform structure. Now I am going to explain the flow diagram of our project. Here in the first stage we designed the CMOS architecture, whether it was in 45 nanometer or 16 nanometer or 35 nanometer technology. Then further, we provide the internal resistivity or capacitivity analysis thickness of channel capacitance. After that, we arrange the CMOS buffer architecture designs. In that stage, the buffer was interconnected with the P-type and the N-type architecture. The values for P-type and N-type architecture, the internal resistance can be varied according to the channel thickness. The channel thickness was varied according to the total overall sizes of the CMOS designs, whether it was in 35 nanometer, 45 nanometer or in 60 nanometer technology. Then in the simulation stage, we provide the input voltages at a particular timings of delay. This will simulate the result and we extract the output waveform structure from the scoped result and provide the check range whether the output timings result was particular conditions of delay performance, and we extract the timing analysis from that output waveform structure of our proposed architecture design. And finally, we extract the total overall voltages at the receiving side, whether there was any voltage drop across CMOS switching devices in the buffer architecture. So here we give the switching effect in the base or gate terminal of the NMOS and PMOS architecture design. The VDD supplies will give flow to the output when the triggering was goes on, and when the triggering was goes to down, then there was no output will be proposed at the output as in the buffer architecture design. Now I am going to explain the running procedure of our project. In the first stage, we design the CMOS architectures of buffer architecture in the layout design. In this, the LEdit, it will display the diagrammatical formats of LEdit for each and every channels in active channel or capacitor ranges, internal structures, N type and P types. This was displayed in the libraries. Then after that, add the libraries by EXT. By clicking the EXT play option, it will extract the library files from our internal structure and describes the each and every color codings of the layout designs. Then press the DRC operation to view any other errors or mismatches of length which are provided in the layout designs. Then after that, we checking the simulation conditions whether there was any warnings or error conditions which are made provided in the schematic diagrams. Then after that, we export this architecture to a SPICE netlist code to generate a SPICE netlist to view the waveform structures of our proposed architecture. After exporting this, we get the coding formats of our layout designs and then run simulation options. Before that, we check the library functions and include the inputs and output port terminals of our project. Then finally, we click the running options in T-SPICE simulation. After that, we view the waveform structures of our proposed architectures of buffer design at a particular nanoseconds delay. So in the initial conditions, we initialize the values of total timings delay for the input circuit, and we finally view the outputs of particular delays which can be measured in the scope result. Thus we designs the layout designs of CMOS buffer architectures in either 45 nanometer or 60 nanometer or 35 nanometer technology. Thank you.